So we will try to recall some aspects of membrane formation. Until now, we've been discussing about membrane processing, some membrane processing. Next spring, we will discuss all the other one in liquid phase, the most important one, reverse osmosis, nanofiltration, etc. But we have been discussing reactors, contactors quickly, and gas separation, etc. All these processes are based on membranes. So the processes are very important because that's the way in which we are using membranes. But if we don't have appropriate membranes, no process. So you have to learn how to prepare membranes, how to characterize membranes, and also you have to learn the optimization of all these membranes for specific application. The membranes you are preparing for reverse osmosis have nothing to do with membrane that you want to utilize in electrodialysis. Or a membrane you are preparing for membrane distillation can be very different from the membrane that you are using in ultrafiltration, etc. Apparently, if you are not an expert, all these membranes can be microporous membranes or dense membranes, and they are similar. But the specific application can be much, much different than expected if you understand the mechanism, etc. And this area, making membranes one time was an art. Today is no more an art because the people now are understanding more and more the intrinsic aspects, the phenomena that are taking place, and so you can really anticipate final behaviors. And we are learning how complicated it is today to predict the performance, but also in the meantime we are learning that is possible. And more people, as I mentioned before, is not more an art, as was years ago, is real understanding, to the point that you will see we can arrive to molecular simulation. That means we anticipate on the computer what we expect at the end of the story. First of all, as I mentioned, membranes. Without membranes, no process. So not only membranes, because the membrane has to be well utilized, but we need to understand. And keep in mind that membranes can be very different in different aspects. In the structure, in the function, in the transport properties, in the mechanism that control the transport properties, and in the material that is forming the membrane themselves. The technology that you can utilize are, in some case, the same technology can be utilized in many areas, but there are many different technology available, and new ones are coming, by the way. Sometimes our technology coming from different kind of process that we transfer to the membrane formation more and more. But to give you an idea, sintering techniques is an interesting technology, has been the first one utilized. I mentioned already that we had a system that nobody knows too much because they were classified for under confidentiality for the separation of uranium-235, etc. They were membrane prepared with this technique. 5 million square meters single plant have been installed for the separation of 235 from 238, uranium-235, 238 in gas phase using sintering technique. Irradiation and track etching is an interesting technique. On the market, you can buy membranes called a nucleopore. These are the only membranes with very homogeneous pore size distribution and expensive, not very flexible. In the sense you cannot change too much the properties, but they are just commercial membrane. Phase inversion is one of the most flexible, largely utilized methodology, and we will see a little bit about. Deep coating, interfacial polymerization, and plasma polymerization are also interesting technology. This interfacial polymerization is becoming more and more traditional in reverse osmosis, for example, or eventually in ultrafiltration. And for preparing also composite membrane, one kind of composite membrane where you have two different materials combined together. And so in this case, you have one membrane can be acting as a support, and you can form a thin layer by interfacial polymerization or by deep coating or by plasma polymerization. That's why we call them composite materials. Sintering and sol gel methods are the one generally utilized for inorganic membranes, inorganic membranes are growing in interest today. They don't compete easily with the polymeric membranes. If polymers are working nicely, don't try to substitute with inorganic. Inorganic are always more expensive. They are much more fragile than polymeric, and it's not easy to tunnel well, not to change too much the property. You will see that with by phase inversion, you learn already a little bit. By phase inversion, we can have the same polymer, roughly the same concentration, the same solvent, just changing the properties or the concentration, or eventually changing from one solvent to the other. The same material can be dense, can be microporous, can be totally different porosity, etc. Cannot be done with inorganic membrane, very difficult. Emulsification support on porous structure, liquid membranes, that can be liquid supported membranes or just emulsified system. Ion exchange membrane, charge groups into polymeric structure. That is what we call cationic, anionic membranes, becoming more and more important in process as electrodialysis, in fuel cell, as you know, that is a protonic naphthalene, etc. Or today, in blue energy production, reverse electrodialysis is based on this kind of membranes. And you can have this system with these fixed carrier and ion exchange membranes basically are the one related to this charge system. So there is a lot of different system, plus someone not listed here, and we will have to update. For example, there are perovskite membranes which are coming now and which are not in the area of inorganic, but totally different in transport mechanism. Nothing to do with traditional transport mechanism that we have been mentioning before. Very different story. They are crystalline material with defects, and the defects are the way for moving some products from one side to the other. So, large area. Obviously, when you just work on membranes, you have to know as much as possible about preparation, characterization, and the parameters which are controlling transport properties can be different. Can be morphology, mechanical properties, chemical properties, electrochemical properties, ion exchange, Donan exclusion phenomena that we have been mentioning many times. Transport numbers can be different between for the ions crossing the membrane compared to the transport number in free solution. And that is also important sometimes to well characterize your membranes. You have been discussing a little bit. Eventually, you will have some other occasion to discuss about. Keep in mind that the membrane material and membrane application and structure are very much interrelated. So this thing you have to know, you need to know a spectrum, because there's totally different way in which you can consider the relationship between material and application and structure. For example, you have a situation in which the membrane material, the kind of material you are utilizing for your membranes, is the most important aspects. And that's, for example, in gas separation, in pervaporation, in reverse osmosis. Why this? Because the mechanism of transport in this system is a mechanism called solubility diffusivity, and you learn about. This is a mechanism which, by definition, if there is a solubility, is a chemical aspect. That means depending from the interaction of the penetrant with the chemical property of the material, you can have solubilization, and after you have diffusion. So the chemistry of the system is very important. If you're talking micro and ultrafiltration, what is more important is not the quality of the material, but is the morphology, the structure of the material. Because here, the transport mechanism is viscous flow or Knudsen diffusion, convection across the pore, etc. So this structure, the morphology of the system, the size of the pore, the shape of the pore, the number of the pore, tortuosity, etc., are more important than just the chemistry, the chemical property of the material. So when solubility diffusivity is present, or when eventually ion exchange property are necessary, the membrane material, the chemistry of the membrane material is very important. But if you have microfiltration, if you are using the system as conductors, exactly what happened also in microfiltration, more important than the chemistry is membrane structure in first approximation. That means it's not in fact, you are using PVDF, or you are using Iflon, or you are using polypropylene, There's not very, it's not important the name of the polymer. It's important how big are the size of the pore. Not chemistry, but physics, final structure. And that can be very important. This in the first approximation. Very often, the two things overlaps. You can also have effect on membrane material on the structure. For example, if this material is hydrophobic or is hydrophilic, that is a part, and also here this can be important. But this is second level of control in the system. So there are these two big categories that you have to consider, where the membrane material is important and where the membrane structure is important. To give now some example, which are the most important properties that we are asking to our membranes and that you have to try to realize when you prepare your membrane. First of all, selectivity. Selectivity is very important together with permeability, obviously. The selectivity is very much related to the both chemical and physical properties. And these are the properties you have to consider is molecular weight distribution, the chain flexibility, possible interaction between penetrants and the chain, or intra-chain interaction, because this is changing, controlling the possibility to create free volume, etc. And that means that in some cases, you can see here, the character of the main chain is important. If you have just a single bond, can have a very flexible polymeric system. When you have a double bond or you have a triple bond, the flexibility of the system is changing significantly. And the same is valid for the nature of the side groups. And if you have just hydrogen on the side groups, basically there's no influence on the possibility of your rotation of the molecule. That's very important, again, in gas separation or also in reverse osmosis to create the free volume in material. But if you have some other groups, as a phenyl group, etc., that is a very significant effect on the possibility of rotation or vibration, interaction of the different chain. So this is the chain flexibility, which is very important for selectivity, is very much related to the properties of the material you are using in term, and you can change this property by introducing functional and lateral group that can change all the rotational energy, possibility of your molecule, etc., etc. And that is what is happening, and that's what you know about. Permeability is, remember that we have subdivided our process between, in the very first approximation, porous membranes and dense membranes. And in this case, when you have a porous membrane, as we have mentioned before, the choice of the polymer is a little bit less important than when you are looking to dense membrane. Dense membrane, the choice of the polymer is very important, is the factor number one. And you can, before making membranes, you can take piece of polymers, put in some solvents, and stirring and checking with time. If you go in a lab where people are studying how to make membranes, you will find a lot of this becker with piece of polymers inside, not just continuously stirred, and you check, because what you are measuring is absorption, desorption phenomena, and depending from the level of absorption, desorption, you decide if this membrane is appropriate or not to make a separation. Because solubility of some of the solvents or salts is issue number one. And there are some chemicals that are soluble. Water can dissolve in some celluloacetate, and salts don't dissolve. So you decide that this material is good for reverse osmosis, because you want to have water dissolved and diffusing, and the salt not dissolve. If the salt don't dissolve, we are sure that they will never penetrate in the membranes, so there will be good high selectivity, basically, if the water, on the contrary, can be easily dissolved. So this is, before doing the membranes, you can make this kind of experiment, quite important. You know that all the polymers, normally, they can pass through this parameter. This is very important. The glass transition temperature is the one when you have a polymer in the glass state, a temperature higher than Tg. This is basically, we call it glass state, and the permeability is very much lower. Selectivity eventually is increasing, but permeability is low. When you are in a temperature lower, you have a rubbery state, and the rubber state is much more permeable in general, but less selective. So sometimes you have to find also good compromise. Crystallinity, in general, we don't like. Crystals are a barrier to mass transfer. So all the material appearing as a crystal at a certain temperature cannot be utilized as membrane, except new materials as perovskite, where just the crystallinity is what we need. But in this case, remember that crystallinity of perovskite today is a problem, can be utilized for selective transfer only at a very high temperature. You can activate the transport only at 700, 800 degrees centigrade, 900 degrees centigrade. In this case, vacancy are becoming the pathway to moving only the ions or the molecule that can jump from one vacancy to another one, from one defect to another one. So crystallinity in general, we don't want. We want to have amorphous material as much as possible. And we know obstacle as crystals. Crystals have no flexibility. Crystals have specific size. But in perovskite, in zeolites are also crystals, and they have a specific shape and size of the windows of the crystal, and that can be utilized to penetrate in some case. So this is in general true, but today less and less and more we can have a new kind of transport phenomena, new kind of material that in some case also crystallinity is helpful. So there is a lot of things. Overall, you have to take care of one problem. You don't want just to make material membranes. You want to make a lot of membranes. You want to operate on this kind of system just by making fibers, making film. You want to control thickness. You want to control mechanical properties, etc. So two things are important. The stability of this material, for sure, but also the processability. And normally these two things don't agree. When the stability is high, sometimes process is more complicated to work on this material. So also here, you must be careful that not trying to look only to stability, because you can have low stability but good processability, and vice versa. You can have a very bad processability, a very good stability. The choice has to be in between, and that normally happens. So you can have some material that are quite interesting, in principle very stable, but not easy to spin any fibers, not easy to cast any membranes of the appropriate thickness. So this is another parameter very important to the point, and at the end you have to find some specific polymers, some polyimide, etc., that have high strength and high rigidity, but in the meantime they can easily be treated and prepared in fibers or in thin film. So that's another parameter. Many polymers have been studied, thousands. Any kind of material has been investigated already for making membranes. However, also here today we are becoming more people giving money for making research in this area is becoming more selective, because most part of these polymers that people have been studying, publishing, they never became of interest. Still today, after 30, 40 years of industrial development of membrane, the polymers we are using are 5, 6, 7. The most are polypropylene, polysulfone, polyether sulfone, polyamide, some polyacrylonitrile, PVDF, etc. But 1, 2, 3, 4, 5, 6, add 3, 4, 5 more. But most part of the commercial membranes are around here, or some variation, some aromatic polyamide different from, instead of polypiperazzinamide can be another one, etc. But the family are very narrow. Publication, huge. But real work on the market. That's why you have to be careful, not just look into a polymer. You have to look at a polymer where you can anticipate and predict. That's the work that we will learn next week, where if you understand what is necessary, which are the parameters, you can try to design the polymer of interest to functionalize one polymer, introducing this functional group useful for increasing the interaction with CO2 or interaction with some of the penetrant that you want to separate. This can be done today if you have good knowledge of transport phenomena, of your final application, level of selectivity, etc., which was not the case in the past. But these are the most interesting one. When you have a polymer, if you have good processability, for example, of interest for some separation, but not good enough for some functions, you can modify the polymer or modify the membranes. You can introduce functional groups, as I mentioned before. This typical case, if you want to have polyether sulfone is largely utilized, cannot be hydrophilic enough. Hydrophilicity, we'll see, is very important in some separation because it's controlling, as you remember we were discussing, controlling the fouling phenomena, for example. So we can increase the hydrophilic character of the polyether sulfone by using some polyvinyl pyrrolidone. This is making much more hydrophilic. And that's one way of doing it. Vice versa, if PVDF, you want to make more hydrophobic, PVDF is already hydrophobic, but not enough, you can lose hydrophobic character, and that's very important in membrane distillation, etc. In this case, you can create another kind of system where you can add, for example, polytetrafluoroethylene, a very hydrophobic material in particles. These are prepared normally in emulsion. So you can mix this fluorinated polymer in a small percent in an emulsion form in a nanoparticle to the PVDF, and you have much more hydrophobic character. And you can find some of these examples of this kind of membrane are already on the market. This one, PVP, some of you is working with PVP already, with other materials, not only with polyether sulfone, but you can use this PVP story for in PVDF or other material. And now this is because it's already in literature, but you can find other kind of additive that can just change some function. This is hydrophilic, hydrophobic, can be just some other kind of function. Can be a tendency to be electron acceptor, electron releasing electron. So there is depending from what you're doing, this can be another way of doing very well stabilized. The reason for doing this is that, remember that we have to make separation, and in all separation, any membrane process, fouling, problem of adsorption, desorption is important, and that's why, for example, when you're talking about proteins, that means all this ultrafiltration of milk or any antibiotic production, etc. If you go in Spain, in north of Spain, in León, there are all the company producing antibiotics is a company sitting there. You will find from many years a lot of everything was done by ultrafiltration. But the main problem is to control the adsorption of the protein on the membranes. And so you have to find a way that as much as possible increasing on your membranes, working for in antibiotics, the hydrophilic character, because that minimize the absorption and make easier the control of the fouling. And then in this way you have to do what has to be done for doing this. In some cases the polyvinyl pyrrolidone or some other material with similar properties. And a lot of these things are not in the paper, because these are the patents, the know-how of the company, etc., depending on the specific separation they want to produce. The technology, I am assuming that this technology you have been already discussing with the previous part of this class, is phase separation. Phase separation is the most versatile, the most flexible methodology, and is appearing in a different way for making membrane. Phase separation basically means that you have your polymer, and you can dissolve the polymer in an appropriate good solvent, and you can have also another solvent miscible with the good solvent, but bad solvent. And if they have a gap of miscibility, these two solvents can stay together in a narrow range, basically. Now, if you and both systems, to get this system of solvent together, they will dissolve your polymer in a solution in a narrow range. Now, if you just expand, you just cast your solution, The good solvent normally, that is the one that you are smart, volatile, quickly evaporate, and so the solution will be concentrated in the bad solvent, and so you have the phase inversion. This polymer will precipitate. This is the general vision of the system. So you have to create a system where there are these two good solvent, bad solvent. Normally, good solvent has to be much more volatile eventually than the other solvents, and this, as much as possible, narrow range of miscibility in such a way that easily, quickly, as soon as the good solvent will disappear, the system will precipitate, and that is what we call phase inversion. How to realize this? Many, many different ways of doing, and the one that I will mention are already obsolete, because if you go in the last review paper I sent you, not mine, but the one by Professor Neil from Singapore, you will find already some new acronyms, because the NIPS and TIPS that in our slide you'll see were separate, now they are becoming one new methodology. They call NTPIS, just NIPS and TIPS together, because the new solvents are appearing with new properties, and the two processes can operate together in the same moment, and that's quite interesting because it's producing new kind of morphology of interest with new kind of solvent we are using. But anyway, this is what is the most traditional system, a homogeneous system consisting of the polymer dissolved in an appropriate solvent in a single phase liquid is transformed through a process of separation solidification in a two-phase system. A polymer-rich phase, solid, the membranes, and a polymer lean phase, liquid, which will form membrane pore. This basically is the mechanism that we are considering. The choice of the polymer, solvent, non-solvent, composition, concentration of the solution, temperature of the coagulation, where after the first evaporation, where you freeze the process, the coagulation bath, and evaporation time, are all parameters that very significantly can change the final property of your membranes. And today, as again, this is no more an art. Now people know how each one of these parameters can change the final property of your system. I was mentioning that there are many different ways to realize this kind of system, and you have what we call AIPS, evaporation-induced phase separation, only evaporation. You just wait that the system evaporates. You can have vapor-induced phase separation. You can have a temperature-induced phase separation. You can have this non-solvent-induced or diffusion-induced phase separation. And you can add here 2 or 3 more of this methodology, which are the combination of, the VIPs and TIPS together. These two together, that can be only one. You can have another one where you have these VIPs, but in under control atmosphere, where you can add something. That you see some membrane that I show already, where we have what we call on-a-camb membranes with a very regular pore size distribution, are systems in which you induce the phase separation together with coagulation of some of the components of your vapor phase, and this coagulation make nanoparticles in the polymeric phase. When you extract these nanoparticles, you have very nice pore size distribution related to the size of the particle that have been induced during phase separation, etc. So this is just the traditional one, but can be more on this. For understanding all this, the behavior of the solution, we can have this phase diagram that probably you are familiar, in which you can have this, all the thermodynamic properties of the system related basically to the miscibility. The requirement of the system here for working is a miscibility gap over the defined concentration temperature range. That is issue number 1, the most important part, characterizing all the system here. The way of doing, very easy, that is just evaporation here. And at one point when the concentration will reach a certain value, you have the separation and you have a solid phase. Or you can have in a control atmosphere, or you can have in just changing the temperature, or you can have exactly the same story in the non-solvent induced, when the non-solvents penetrate in the system, etc., etc. All these can be studied for different thermodynamic aspects through the phase diagram. The phase diagram is very important. I'm assuming you know already something, but consider the thermodynamic aspects can be well understood in the phase diagram, but the real formation is not only thermodynamics. Most important can be kinetic aspect. In the phase diagram is telling nothing about the kinetic aspects. That's why you have to know about the thermodynamic, so you can predict at which temperature, at which concentration the phase inversion will take place. But you cannot predict the final morphology and property of your system, because the kinetic aspect can overlap sometimes the influence of the thermodynamics. You can have something unexpected in terms of thermodynamic aspect, because the kinetic aspects are changing a little bit the situation. And that's why that is important to know about all the different mechanisms that control the system. Basically, the people working in this area have been always characterizing the phase inversion process through two kind of mechanisms. In principle, you can talk about a delayed demixing. When you have the demixing, that means the phase inversion can be delayed demixing, where you normally form a porous, often closed cell, macrovoid free, so no fingers, substructure with a dense, relatively thick skin layer. So an asymmetric membrane, that is very important. Both systems are forming asymmetric membranes. That means it's not homogeneous, except if you have this complete evaporation, stage number one. In this system, normally you have delayed demixing or instantaneous demixing. In both cases, you form a porous with a dense, relatively thick skin layer, asymmetric system. That was the big invention that made membrane formation a big industrial sector. To be possible to have a membrane where only very thin layer at the surface are selective and permeable. The rest is a support. Or you can have instantaneous demixing. Membranes show a high porous substrate with macrovoids. No macrovoids in this delayed demixing. Macrovoids are present instantaneous. And finally, porous skin layer, not a dense skin layer as is here. So the two systems can be very, very different. And going from a delayed demixing to instantaneous demixing is to do with the kind of solvent, with the relative affinity of the solvents with the polymer, or between the good solvent, the bad solvent, and the polymer system. So changing this, you can change completely the performance of your final membrane if you understand what is going on, which is not easy, but today more and more is easy to do. You see that the solvent, non-solvent affinity, and the solvent concentration, the coagulation bus, is dominant phenomena that control the final property morphology of your system. And the fact that in the good solvent, non-solvent miscibility, the latter, that means the non-solvent, can easily penetrate in the casting solution and create a porous structure. That is one of the points of interest if you want to have a porous structure, basically, etc. Just to show you, by the way, remember again, this delayed demixing, a process in which a dissolved polymer in solution, with or without additives. Additives can change completely the scenario, by the way, shows a delay phase separation after immersion in non-solvent baths. And that means there is a certain time interval between the moment of the immersion, and this certain time interval is very important. If you make membranes with this system, check how many seconds, or tenths of a second, that you are operating, because this is a parameter. If you change this interval, air gap, when you spin your membranes, you are changing completely the final morphology. And your colleagues that are spinning, they can tell you how significant is this effect. And between the moment of immersion of the polymer solution in the non-solvent bath and the onset of liquid-liquid demixing. Vice versa, when you have this, you can have delayed demixing when the interaction between solvent and non-solvent is poor, and the dense top layer and isolated pore in the sublayer are formed in the final membrane, etc. Okay, these are all these. just to show you how significant can be the effect. The same kind of membranes and changing the non-solvent from water and going to non-solvent as ethanol or going to butanol, you can go from a dense membranes at the end, just using the water, but if you just increase the affinity, going to ethanol or butanol, you just induce porosity, and that is asymmetric with a layer. You can change the thickness of the dense, and that at the end can be totally porous. At the same temperature, at the same level of concentration, with the same polymer level of concentration. So if you understand this, and you change the solvent, etc., this is quite interesting, because you can, in principle, prepare any kind of final morphology. That can be ultrafiltration, microfiltration, that could be a pervaporation membrane, for example. That would make a lot of sense, and it's quite interesting if you know how to do it on large scale. Part of this story, the thermodynamic aspect, at which temperature, at which concentration the phase inversion is taking place, is present in what we call this ternary phase diagram, where you have the polymer, the solvent, and the non-solvent, and you just to certain temperature is constant in the system here, you can have an homogeneous region, depending from the different concentration, they have a homogeneous solution, and you have a region where you have the possibility to have a demixing in forming a polymer-rich phase, the membranes, and the polymer-poor phase that is just the what we call the empty space. That means the porosity of your system. And this line here, that is the binodal, the different system. Okay, that's the definition we gave already. The polymer-rich phase is the phase of that phase of a two-phase equilibrium system consisting of a polymer and a low molecular weight material, in which the polymer concentration is higher, and the polymer length is the phase of a two-phase equilibrium system consisting of a polymer and a low molecular weight material, in which the polymer concentration is lower. Keep in mind that this is a clearly written two-phase. If you, for any reason, add a certain component, for example, additive, titanium, you make a mixed matrix membrane, etc., and based on some polymers, this phase diagram can also be different. Because this is a two-phase system, as if you have an heterogeneous system with some additives not soluble. Case of titanium dioxide is typical. A lot of people are working on titanium dioxide or similar, graphene or zirconia or silica, etc. You have to also to recheck the phase diagram, because that can be different. Because this clearly written what we are talking about, and the third component can change all the situation. So you have to know about. That is at the end what you can obtain. And keep in mind that this plot here is the binodal, the nodal curve, is the curve of coexistence, where the two systems are in equilibrium. The homogeneous system and the system where the phase inversion can take place. And this is the binodal curve. Binodal or coexistent curve denotes the condition at which two distinct phases may coexist, homogeneous and heterogeneous. Equivalent, it is the boundary between the set of conditions in which it is thermodynamically favorable for the system to be fully mixed, and the set of conditions in which it is thermodynamically favorable for it to phase separate. Okay, so this is one of the things that you can build up, and you have to learn how to make this kind of phase diagram. And all of you working on making membrane, step number one, they learn how to make the phase diagram for the system on which they are going to work. And the phase diagram, by the way, this is the binodal is defined the condition with the chemical potential of all these solution component is equal in both phases, in each phase. The extreme that's down here is the critical, critical point in which the spinodal curve and is just formed. There is another curve that you have to know, and is the process that when you have the separation here, you can have the crystallization, gelation, vitrification, and that's quite also important, because that will control the final form. This binodal is the equilibrium. It's not for the spinodal curve. The spinodal is the one where there is no, the system is non-stable anymore. There is the separation by definition, no equilibrium at all. And that is the nucleation and growth is the process of moving towards equilibrium by droplet nucleation above spinodal curve. And the spinodal composition is a mechanism by which a solution of two or more components can separate in distinct regions with distinctly different chemical composition and physical properties. Okay? So all this definition, I am assuming that you have been discussing a little bit, so you know all this kind of phase diagram. Remember that when you can have in this depending which region you are working, for example, in the region here, in this metastable region, you have just nucleation and growth. When you are in this region, when under the spinodal decomposition, you can have a different form of nucleus growing or spherulite, etc. So that is also important to know in which area you are working, over or lower than the spinodal curve. Okay? Anyway, phase inversion, I think you know already how to do it, because that is the simple mechanism that we were using years ago. Now you have this optical system that just make a registration of the when opalescence is appearing, etc. At my time, you had to watch and see what is happening, and depending from your capability, experimental capability, you are building up this. But basically, that is the system in which you are adding the non-solvent to the solution and looking at the moment in which at a certain temperature this phase inversion was taking place, and at that moment you are just making the point. Looking here at which ratio between the dropping of the non-solvent in the solution where you put some polymer, polyether, ether, ketone, Chinese polymer, unknown, nothing in the literature, so you have to do everything by yourself. And depending water, dimethyl formamide, and peak, and then 1 point, second, third, etc. And you are building up all this. That's exactly what some of you are doing normally, but more and more you have to do, and learning to do better and better, and understanding if this mechanism is the one that is really controlling, or the kinetic of the precipitation, etc., can be also very significant. That's what people are doing today, because that can be quite interesting. And that's a typical case in which you can just study with, for example, changing to see how the solvents can have an influence. These are 3 phase diagrams in which you see how the system works when you are moving from one solvent, from dimethyl formamide, dimethyl acetamide, or Teflon, or THF, and you're totally depending DMF, DMA, THF, totally different kind of final morphology. Just changing the case. Okay? Here the same case I was mentioned before, how the different coagulation baths, that means going from chloroform, alcohols, or a different kind of alcohol, methanol, ethanol, isopropanol, butanol, again. Higher alcohols give membrane with much thicker dense top layer. So if you know how to do it, you can, as we saw already before, remember with the 3 alcohols, water and alcohol, we can change the thickness of the top layer just by changing this kind of the property of the non-solvent. That means the affinity of the non-solvent. The membrane increase with increasing molecular, the thickness of the top layer increase with increasing molecular volume of the external non-solvent due to the lower diffusion rate, which leads to delayed liquid-liquid phase demixing. So these are all components that are controlling this kind of preparation. Changing temperature, all these phase diagram were one temperature. Now you can change temperature, keeping constant concentration, kind of solvent, etc. And also here you can see you can just change from 20, 35, 45. You can go from 0.6 microns to 0.035 microns. You can decrease significantly the thickness of the layer. So another parameter that just keeping control of the system. Coagulation temperature acts upon the physical state of the cast film and is expected at a lower temperature, 20 degrees, cause a decrease in the rate of solvent-on-solvent exchange and causing a delay in polymer precipitation and decreasing this macrovoid formation, etc. So all these aspects can be predicted and utilized for designing the kind of final membrane that you want to realize. You can change the rate of precipitation by different coagulation, by changing the composition of the coagulation bath. Instead of making only one, you say 90% water in glycerin, or you can just start for and arrive to 10% water in glycerin. So you can add some addition, and again you are changing the relative extraction and diffusion of these solvents in the polymeric matrix. Changing this, changing the relative affinity of the system, going from just glycerin to water, 10% of water in glycerin, or here is about 90% water and not too much glycerin, you can significantly change the final morphology. One of the problems you want to solve is the formation of macrovoids. Macrovoids, in general, we don't want to have, because mechanical properties are changing, and the lifetime of your membrane, stability, compaction, etc., are problems. So this is one of the things how to avoid the macrovoid formation, and there are different ways of doing this. Macrovoids normally are observed in systems where instantaneous demixing is taking place. And that means you can find a way to try to change what is inducing this instantaneous demixing, as we saw before. With the formation of macrovoids in membranes from a polymer solvent non-solvent system can be suppressed by choosing a solvent non-solvent couple with a low tendency of mixing each other. So if the tendency of mixing is relatively low, that can be a way to have this, because you just control the instantaneous demixing or delayed demixing. And that is one of the things. Basically, there is the system to reduce macrovoids is normally you have membranes with macrovoids, without macrovoids, in case of delayed demixing. And the membrane with macrovoids are formed in case of instantaneous demixing, as we saw already before, except when the polymer concentration and the non-solvent concentration exceed a very low value. So also these rules are not 100% valid. So the system is complicated because the possibility that you're trying to avoid the macrovoids by inducing instantaneous demixing can be related also to the amount of the non-solvent concentration in the system. That means macrovoids normally also are formed, but they have to grow. So you have to find a way to control the expansion, and that is a problem of diffusion. And that's why there's if you want to inhibit the macrovoid formation, normally you have to make the solution easy to gel, for example, or adding the solvent to the coagulation bath. That means you have delayed mixing, or sometimes you can have some additives on the casting solution. All the systems are just changing the relative velocity of extraction and the different affinity. Just to remember quickly, this phase inversion, the most interesting, the most versatile, the most complicated if you are looking to all the parameters. And some of you that are working on this, they are learning. Now you want to change solvent, for example, for a green phenomena, and traditional membranes can be prepared with new solvent. Point number one, you have to study again all the system, because if you change the solvent, you are changing everything. And the new phenomena can appear that you have to keep control, because this changing can be the relative affinity of the good solvent, the non-solvent and the good solvent can completely modify the final morphology of the system. In general, we can use this system for making a lot of membranes, phase inversion, and you can make symmetric. I showed you before, the same solution, you can make symmetric or totally asymmetric just by changing the kind of alcohol you are using at the time of evaporation, etc. Symmetric, asymmetric, a lot of things can be done. So this is the most versatile as I was mentioning. And we can also change the size of the pore, or having a dense membranes, and that is typical case you can see here. And this is another case in which using a modified phase inversion, a lot of it to be done in this line, but that's something we already published a few years ago, you can have very nice homogeneous pore size distribution. If you're able to produce on large scale roll-to-roll film of this kind, a lot of problem in principle can be solved. However, that is not just typical, it's a paper, there's no membranes of this kind available. There's a lot of work to be done because mechanical properties are still low, they will break easily. So the paper, nothing happened, but in real life a lot of trouble exists. So we have never been able to utilize in real process. I hope in the future, but this is work to be done. And here, kinetic aspect and thermodynamics are helping a lot. So you have to keep control on both kind of aspects, but it makes sense. If you realize this, membrane distillation, etc., will have a lot of these benefits. Let's leave this technique, and we have to see how can be done in a different form, other kind of methodology. By the way, composite membranes, I was mentioning, you know already, all the membrane, when they are asymmetric, they are not composite. In fact, they are asymmetric. Apparently, there are two different layers, but this is intrinsically asymmetric. Same polymer, different morphology. You can prepare completely different membranes, that the one we call composite membrane, when you have the same final morphology, apparently, but two different materials. So in this case, this is what we call in situ polycondensation, interfacial polymerization, deep coating, different methodology which you can combine expensive polymers, Iflon, with less expensive support. So the very, very controlling layer, 1 micron and less of the expensive polymers, it can be acceptable if you just have not too much polymer to be utilized when you have good support. Or most part of reverse osmosis membranes today are just produced industrially using this kind of methodology, in which basically you have a porous support, and with different methodology you can form a selective layer on the surface. That can be polycondensation or can be just some other deposition of the barrier layer on the surface of the porous support. And that's so the first step is just to have the porous support. Ultrafiltration, microfiltration, PVDF or polypropylene or some polyester are typical example. And after this, you have to coating of the porous support by a polymer, reactive monomer or prepolymer solution, followed by drying or curing with heat or radiation. So you just make the pre-polymer or just and you induce the reaction by temperature, by radiation, by curing, and one of the methodology. You can also use this by plasma deposition. You can have your system and you can just induce on the porous support formation of very, very thin film for gas separation, for example, just by discharging plasma. Or interfacial polymerization of reactive monomers on the surface of the porous support, and that is the most utilized technique today for making reverse osmosis membranes. This is a patent by Cadot, long time back, and the one that we call these TFC membranes, which are the very well utilized aromatic polyamide, are the ones that are formed. We started from polypiperazinamide. This piperazinamide, which is also one of our patents, by the way, the formation mechanism is composite membrane by interfacial polymerization of piperazinamide with 3-methyl chloride. That's still today a lot of the membrane utilized industrially are related to this kind of reaction, in which you just form this polypiperazinamide, just a thin layer on the surface of a porous support, which can be polysulfone or polyether sulfone or PVDF and similar. If you like to, this was quite interesting and important for one reason, because at that time, when people were looking to make membranes stable to chlorine, because chlorine is was still today, but not in the future, was largely utilized in disinfection of water. So to treat your in reverse osmosis, your membranes with chlorine was standard methodology. Most part of the polyamide are sensitive, and the cellulose acetate itself are sensitive to chlorine, so they can be easily destroyed with time. Washing every day with chlorine, etc. So everybody was looking to material much more stable to chlorine. It was a way to have money for a project with this very stable material. Piperazinamide is one of the most stable aromatic polyamides stable to chlorine. Today this problem is over because chlorine is banned. And more than this, will be banned, it's not yet banned, but will be banned because there is a lot of phenomena related to the chlorine in your body, interaction in nature, etc. Chlorine by itself is not dangerous, but the metabolism of this product can create problems that we have been learning now. So the problem is much less severe now. You have to look. Second, chlorine is inducing biofouling. At that time, biofouling was not existing. In the sense, people were not understanding what was biofouling. Today, we know that the chlorine, when you have too much chlorine treatment, you are inducing more biofouling than you control fouling eventually, or you sterilize the water, but you induce biofouling. So chlorine is disappearing. That means not only piperazzinamide can be utilized, but if you have other ideas, forget about chlorine. There is no more motivation for doing this. Anyway, this is the mechanism, and you have just the preparation of the system, the schematic of the preparation procedure of this beta CD polyester nanofiltration composite membrane, and that is just by interfacial polymerization. This is coming from a patent. This is just, oh sorry, this is totally different. I may make confusion. This is, you can use something similar for improving the anti-fouling properties of your membrane by creating a beta-cyclodextrin polyester thin film in nanofiltration membrane. That's another work that we have been doing. That's why it's mentioned here. And it was apparently, I was thinking, the same story that you are doing is in Cadot mechanism. But this is for entrapping. There's another sophisticated, elegant way, difficult to realize on large scale because beta-cyclodextrin are expensive, but that can be possible. If you want to functionalize better your membranes and inducing some specific selectivity, these beta-cyclodextrin are very, very selective compounds. And you can prepare membranes where you have an anti-fouling layer of beta-cyclodextrin on traditional support. Expensive, but quite effective. Not easy to arrive to industrial system. That was interesting because now you can induce some specific, with these imprinted composite membranes. Normally polymers are not very selective. So except for the case of water sodium chloride, desalination, and other case, or bivalent, monovalent. If you want to have some specific separation of some compounds present in solution, pharmaceutical industry, for example, you must be careful because normally our system don't work, particularly when very low concentration. You can solve the problem by very elegant, specific functionalization of the dense skin you are forming. That's the case. You can have what we call imprinted composite membranes. And imprinted composite membrane can be utilized in chiral recognition. You can select between the level form and the right form with the system, just producing some membranes in which you induce memory to this imprinted composite memory to the membranes for a specific selectivity. This is not selectivity of the polymer, it's selectivity related to this, what you are putting in, this functional monomer, basically. And that's quite interesting, and it works. Also here it's not very easy to make the large-scale production, but can be done, and if you go in the literature, in pharmaceutical and biomedical acta, that means this is very, this cannot be sodium chloride, obviously, but there is some specific pollution problem related to production of drugs, etc., which are very severe today. This is one of the possible way of doing, and you can use. Plasma polymerization, I was mentioning, is another way to form this composite membrane, and if you have the plasma, this can be just starting from some monomer, you can just produce the polymer, and you can just have a very high density for this polymer on the membrane surface. This is the technique, expensive for gas separation, has been tested. And there are different of these things. Another way of doing membranes, largely utilized, and some of you, depending from your shoes, is just to combine the the formation of your membranes with stretching. Stretching at a certain specific temperature, normally higher than the TG, the glass transition, you can induce the formation of. You can extrude the film, and during the extrusion, you can, that can be perpendicular or longitudinal, that can be in both cases. You can have a very nice distribution. This is Goratex. A lot of you is using, buying Goratex. That is the way of doing. Today, some of you is working with some other materials similar, and when they finish to produce these, I don't know, membrane fibers, this material they know is going to be stretched, because stretching is a way to modify in part the initial porosity, eventually giving all this orientation, depending in the way in which you are stretching, or increasing. If you have 60% and you want to arrive 85% without destroying, if the material is good, that can be a way of doing. Largely utilized, Goratex are produced. If you do something similar, keep in mind I mentioned already, I repeat, in this country, I don't give you the name, but there's a company utilizing 5 million square meters of this membrane per year, every year, and they hope they will make 10 million or 15 million, but they are looking the membranes. And they have to buy abroad, etc., and then they come to the university asking, why don't we produce these things? And no one is able to do on the large scale. But you can, if you are able to produce your film, stretch in the right way, etc., you can have the corner company, Korean company, looking for at least 5 million square meters per year. And maybe 10, 15, 20 if things are improving. And by the way, keep in mind that the same kind of membranes can be, the same kind of material can be also produced by thermal phase inversion, where you don't have such a nice oriented porosity, is Acurel membranes, but very similar level of porosity in a different morphology. And that's also changed the final performance. This is, for example, this is the stretching operation. The A and B, you see aniaxial, very, very clear. This is just in one direction. This is biaxial. You see this is the different than in the final, the totally different the kind of distribution of the porosity compared to this one. That's very effective. Some cases, this stretching is done during the formation. Some other cases done after the formation. You produce first, and after you go to another machine as a post-treatment. Instead of making thermal treatment, as you do with some other polymer, you make a mechanical treatment. This is a kind of annealing of your final membrane to change level of porosity. You can change the level of porosity by thermal treatment, TR membranes you are studying here, or by mechanical treatment by stretching behavior. Not all the membranes can be stretched. Most of them, if you do, you break, you destroy the membranes. So you must be able, I was mentioning in the beginning, one slide, be careful, processability and stability. That's the case. You have to be able to understand how much can be done in terms of, without destroying the material. And these membranes, as soon as you prepare, you're very accurate, delicate, you don't treat too much. The first test they do when you give them sample of your research results to keep your membranes that you are treating as a baby, and they put in a machine, they will make 5,000 stretching per minute. And they're terrified because they have to simulate, for example, what is happening to you when you're living. That has to be for years before breaking. So they have a machine that is doing in a second, so your poor membranes is destroyed very quickly, but that's what has to be done. And finally, they can find something that really works, and they say, no, that is what is happening. You have to induce some interesting morphology in the system that give mechanical properties appropriate for making real operation. But can be done. Can be done. So, sintering, I told you, first technology producing membrane on large scale has been this one. No phase inversion at all, powders. Powders heated and press. And at that time there were a lot of stuff. And you can also produce level of porosity, but you don't have 0.2, also not just 0.2, but the quality of your membranes is very difficult to be controlled in this way. You can have, in principle, from low porosity, 0.2 microns to 20 millimeters, and these are mainly microfiltration membranes, also for gas separation. Very difficult to control. If you want to make a 0.2, 0.3, 0.4, forget, no way. Everything depends from the quality of this powder. Today, compared to in the 60s, when people were doing this work for this, this was nickel powder at that time. Very difficult to have homogeneous nanoporous material. No technology. Today we have. So you can also improve significantly the control of the pore size using this sintering technique. And that is the system that they were all symmetric, porous, and the material used was polymers or stainless steel, tungsten, aluminum, carbon, silicalide, sometimes mixture of this with pore size distribution from 0.1 to 10 microns, 10-20% very low basically. And but that's some of these, that's also polymeric powder, but can be just also Teflon. Teflon, that is not easy to dissolve was done by something similar, some sintering of this kind. And trash etching is a totally different story. The sense that you have your membranes and you have radiation, cosmic radiation. The radiation comes, or you put in a nuclear reactor system, they can have this kind of radiation. So you induce some chemical attacks, some energy attack on the membrane surface, and just very regular normally. After the second step, in which you have some etching, you have chemical treatment that is dissolving what has been in part destroyed by the radiation, and at the end you can produce this kind of membranes. This is polycarbonate, this is nucleopore membranes. These are commercial, expensive, small scale. You cannot make big module, etc. normally because for the cost, but you can see here the size of the pore is very regular because you can tunnel depending from the power of your radiation, depending from the time, the intensity of the radiation, and the time that you just just focalizing on the system, and that is what is happening here. You just change the size of the pore, and after in the etching bath you just dissolve, and you have at the end the membrane coming out in this way. That's quite interesting. Small size, normally you buy these membranes in just for the lab scale or in a medical school, in biotech, etc. It's difficult to have a big module for the cost, but interesting. As you know before, we are trying to have the same morphology, eventually better, using phase inversion. And that's very elegant, and you can easily, you have to avoid these kind of things. You see here by etching, sometimes you have two pores, two nearby, and they merge in one, so it becomes double. And that is destroy for specific application. So phase inversion can be well utilized for improving this kind of system. Not easy, but we are working exactly on this basically. And okay. Porous membranes asymmetric by deep coating is another technology that can be utilized. You can use a coating of a layer on support membrane as a means to surface functionalization of this. And you take an asymmetric membrane already prepared, can be PVDF, etc. You put in a coating solution, anything that you can form this thin film on the surface, and this thin film layer will be absorbed on the surface after this or solvent evaporation temperature cross-linking with sodium, also some glutaraldehyde, etc. that cross-link the surface. That can be also utilized also for enzymes coating sometimes, and that can be one way also of doing. That is a simple, theoretically simple way of doing. You will find it in notes. That can be also utilized. And I was trying to arrive. That is one of the areas of interest today is to make these mixed matrix membranes. And some of you are involved in the preparation of mixed matrix membranes. For any kind of application, can be gas separation, can be ultrafiltration, can be reverse osmosis eventually, etc. That's why it's quite integral. It can go from fuel cell, gas separation, pervaporation, MBR, reverse osmosis, everything basically. And a typically interesting case is the titanium dioxide. That's the one that you can find more in the literature. So just you can find, but this is not just titanium dioxide. There's a lot of similar stuff. If you just want to make something different from what the other people are doing, you can just check something. Titanium dioxide is interesting because you can, as you know, this is a catalyst basically. You can use solar energy to activate some chemical conversion and the way to use energy. And that is a typical reaction in which you can just form proton and electrons. And that is if you just work on this kind of system, you just have what is called artificial leaf. You can produce artificial light as can utilize and the artificial leaf, because leaves are the one that plants are growing, taking solar energy and just this kind of process without titanium dioxide, but there is other stuff inside that's just able to interact the oxygen and the water and doing this kind of reaction that are the one in which we are living, chlorophyll, etc., related to this. So this is quite interesting, and starting from this, people are trying to prepare titanium dioxide mixed membranes. If you go in literature, you will find in Europe there is a big project today. One is called NAWADEX, where we are involved, in which you are using titanium dioxide ultrafiltration membranes to try to optimize reverse osmosis. It's a way to better control of fouling. So in the pre-treatment, not only are you using UF, you're using UF with special membranes. This is a mixed matrix membrane where titanium dioxide and some other stuff is inside and eventually complicate, but this is a way of doing. For doing this, you have to check the percent of this additive you can put, the affinity of this additive with this polymer you are using, not easy. Remember that when you are talking about catalytic membrane reactors, I'll show you the situation, some membranes. We want to have an homogeneous distribution at very high level of this additive, because this is one active, difficult. Much easier to form clusters, not very well distributed, etc. If you want to do what we need, you must have to think about and solve the problem. For example, I'll show you some example in which we were making on our polyoxymetallate. We were putting some added some fluorine compound, complicate one, but fluorine, and what was before a bad cluster became a very nice homogeneous distribution. If you do this and you're able to do with titanium, etc., these are quite interesting improvement what people are doing today. That's what people are trying to do. And so you can have a way to metabolize, for example, phenol. Titanium dioxide is quite interesting to destroy phenol, which is difficult to remove in other way, and that can be one of the way of doing. And if you want to do this is a complicated procedure, but you can go in literature, you will find the way of doing, and you can have there's coagulation baths and dipping the membrane titanium dioxide suspension after pretreatment with pretreatment. Now you understand why, because we need to change the affinity, and the pretreatment is the way to change the affinity. And post-treatment, just the treatment to consolidate and to give strength to the membrane you have been preparing. So these are just some things described, some other one is not described because patents are present, but you can just make some interesting membranes by starting from the preparing your solution, casting, coagulation, thermal treatment for giving the final mechanical properties, and it's quite interesting membrane can be prepared at the end. As I was mentioning, there's a lot of this. This is what some of you and a lot of people around the world are trying to do today. But that is another way to introduce some additional functionality to the traditional membrane we have. Graphene, you know what is graphene? That you can have graphene and graphene oxide. Graphene basically is, instead of having a three-dimensional carbon nanotubes that are more familiar to you, just this carbon structure, you can have a bidimensional one, very thin film. These things normally are very impermeable. It's not easy to have something going through here, very small for most part of the product. However, in some case, still something can be done, but it's easy to induce defects here. So you can create defects just on the graphene, by the way. Or you can use a layer, multi-layer of this graphene, and having this selectivity is related to this space between different layers. So you have to know how to control this the space between different layers of the graphene, and that is induced in some selectivity. But already this structure with eventually defects is quite interesting. You can have graphene, or in this case graphene oxide, that can be utilized for gas separation, but you can use this as graphene for example, membrane distillation, or people are also looking for reverse osmosis. Quite interesting, difficult, nothing still exists, but this structure can be quite interesting combined with what we have already. Projects are in progress in this department, by the way, and all around the world, basically. And the motivation are clear, and you can also have these oxygen-containing functional groups, including epoxide, ketone, carbonyls, and that is just giving some functionalization to the system and inducing some permeability, the one necessary for the separation we are also working. Functional side grooves bound to the surface of graphene sheets may improve interfacial bonding between the graphene and the matrix. Exactly the same problem we had with titanium dioxide, with any other kind of additive, if you want just to distribute graphene in a traditional polymeric phase, which is another way of doing. The two-dimensional are expected to offer promising nanoscale filler for the next generation of materials in general, membranes specifically. And, okay, yeah, many. Aquaporin story you are familiar probably with. You can reproduce, this was a Nobel Prize, a guy understood how water is moving very fast and selective across our biological, cell in our body. And people understood, and they received a Nobel Prize, and there was one protein, aquaporin, that is forming channels. And depending from the affinity and the size of the channels, water channels are present in this aquaporin across these biological membrane, the cell membranes. So everybody now is trying to reproduce aquaporin protein to extract and to concentrate and to add, instead of titanium dioxide, etc., add aquaporin. Or to produce some other chemicals, not this protein, but other one having some similar properties. So this is an interesting field. I don't think it will be available very soon, but in perspective is a way of doing. There are companies trying to sell you membranes with aquaporin already. Don't buy, because I don't think they will work very nicely, and the cost is quite significant. However, this is trying to attract investment for research based on the reproduction of this structure here, which is interesting because for sure they work in all of you nicely. How to reproduce on large scale is a typical, is not so easy, because you can see also here that people really understanding in detail will have another Nobel Prize. See today, the selectively, very selective transport of water to in a single file, well, transport of ions is abrogated by an electrostatic tunneling mechanism of the channel interior. And the aquaporin acts as a water channel which selectively allow only to water to go through. This is a very approximate modeling at the moment, and is not 100% clear why it's only water and not, for example, some alcohol. Some other hydroxyl group can have the same behavior. Anyway, there is a quite interesting model, and people are trying to work this, to try to biomimetic membranes which just reproduce the one existing in nature. Another kind of membranes, dynamic membranes. This is much more general than expected. That's why I mentioned, keep in mind that when we are talking about fouling phenomena, formation of some deposit, some film, if in some case, and it became industrial, years ago we were studying this, many, many years ago, you can see here, and just to form, dynamically formed membranes. And in nature, in industrial application, after this, people were producing union carbide, was producing on some microporous film deposit of some chemicals, some hydroxide, alumina, iron, etc., to treat textile water. You can form first some dynamically formed gel layer, and these are becoming selective and permeable to specific compounds. So Union Carbide, the big company, they were producing this nice module, and they were using this for the clarification, purification of the water from textile industry. The reason was that they had very nice tube, carbon tube, stable high temperature. Textile industry discharge 80 degrees centigrade, 85, not easy to use normal ultrafiltration. This dynamically formed was stable with the temperature. And that became a system. Today, more and more, this can be present in bioreactors. In bioreactors, you can form gel of your enzyme, and people are using more and more the same concept. You form and dynamically form, because during ultrafiltration you have a deposit. Instead of trying to avoid, you try to control the thickness and the quantity of stuff. And when you have the film form, you operate this, you send your solution. And eventually, when you release the pressure and the cross flow, the system redissolves. So in principle, you can also regenerate your membranes and your support with time. Interesting concept, long time back, no, it's still, but today is coming again and working again on the same line. All these inorganic composite membranes, remember, and we will stop here, that's quite interesting because all the inorganic membranes available, they are the same story of these asymmetric polymeric membranes. The real interest for inorganic membrane came when people have been able to reproduce this kind of morphology. So a big support, porous, and thin layer, all inorganic. It's not just by polymer, etc. These are just, in this case, polymeric salt, but the wrong example. But normally you can do the same by different level of inorganic material. It's possible today because now we know how to produce, as I was mentioning before, nanoparticles of silica, alumina, etc., of different properties. So you can have the same material forming this kind of morphology, and depending from the very selected uniform nanoparticle of nano size, basically, you can form the other layer. At the end, you have just an asymmetric inorganic membrane. Don't read here just this there is some polymeric salt. You can do exactly the same with all inorganic materials, with suspension basically. And or you can also use as a polymeric salt titanium oxide and alumina titanium oxide in a colloidal salt and particle suspension at the end. And this is just the way in which you can prepare. You have the ceramic powder. You create your suspension. Eventually, you put your polymer binder surfactants to promote a better aggregation. And on this suspension, you just cast your membrane, and after you go to the drying, or after drying, you can have annealing, high temperature, hybrid organic and organic green membrane, and after you have desintering. If necessary, you just press high temperature. Same story of the 5 million square meters of this uranium-235, but this one today are becoming large-scale production. Without not with the same material, the same scope of long time back, but if you go in a different place of the world, these kind of membranes are becoming available, also flexible, which by definition is strange because ceramic is not flexible, but you can produce some of this that you can roll also with some special material, playing in this step here. The polymeric binder of the surfactants during this starting, but you have to start from ceramic powder. And the quality of this powder is issue number one. You have to, if you are able to have different layers of different size, monodisperse, you can have a perfect nanofilter, not reverse osmosis, but we can have nanofiltration membranes, ultrafiltration, microfiltration. And that's in France, there is a lot of work in Montpellier. And that is the flow sheet. You can have different way of doing also this. That is a salt gel process for having a membrane, that's for the nano membranes producing smaller size. And there is a different way of doing that. At the end you have this interesting, and you can just go through a colloidal salt or a polymeric salt. Depending from the chemistry of these two solutions, you can you form a colloidal gel or a polymeric salt, and after you have the drying and the sintering, basically this methodology is all the same. Remember perovskite. The perovskite is totally new, totally different, not existing on large scale at the moment, but a lot of people are working more and more because the perovskite have very good electroconductivity and oxygen permeability at the moment. The perovskite we know. The possibility that instead of oxygen, this membrane, this material can have some other selectivity exists. Can be hydrogen, can be, I was mentioning lithium, can be strange story, and we don't know yet. They have potential application, potential for oxygen separation in steam reforming of methane, I told you, and there is the way of doing. Now we know how to produce the perovskite powder. When you have the perovskite powder, the mechanism of formation of the membrane is similar to the one we have been discussing before. The chemistry is different, but the logic is the same. So you can have a different way of doing with citrate, solid state co-precipitation of the different compounds. This you can find in literature. But if you want, you can try to modify these things and having some other chemical species, some other salts, some other raw materials, introducing different kind of metals, and having new kind of perovskite eventually that don't work, are not activated in the defect at 900 but at 500. And that would be very, very interesting. Has been done for superconductivity. So this is something that is not so crazy. And after you make the same kind of chemistry on the system, you produce your solution with your chemical inside. After you're stirring, heating, you have this, you mix citric acid with the solution containing all the different salt and oxide, and you just produce a powder. And after you have this pressing and annealing at the end, you have this kind of perovskite powder, pressed, sinterized basically, as we were doing years ago in some other case. Quite interesting. Zeolites, just to know, we don't have too much time today anymore, but we will discuss eventually in the next year. This is a very old story. That I don't like to mention too much, but my first publication in '67, no one here was born at the time. The title was Zeolite Membranes, exactly the same title, but it was '67 you find in the literature. And that means nothing new. However, today is becoming new again, just because we are learning a lot more. We need, again, this material, and you will see that for fuel cell, for steam reforming, and gas separation, zeolites are becoming, again, interesting. Why this? Because zeolites, first of all, they are in nature. And in nature, they are working as membranes in many cases. They make selective transfer of cation ions in a lot of phenomena underground. And so they are interesting, but they are crystals with a very specific morphology. This is a faujasit, and you see here, they have some windows. These external, all these are crystalline material, so they violate what I was telling before. We want to have amorphous. Perovskite, no, are crystals. Zeolites are crystals. We are just using the size effect, basically, step number one. There is other effects more than size, but the first one is size. Because if you want to penetrate here, you must be able to enter in the cage, which is on the back, and there is some windows. And these windows have each one of these material. When you see Faujasit has a window of 7 Armstrong, 5 Armstrong, 3 Armstrong. And this number 3, 5, 7 is the one that is combined with the name of the zeolite sometimes. That means that if you have any molecules, 11 Armstrong will not enter, because you have to destroy the structure. Everything that is lower than 7 will penetrate and will be activated with the sword, will separate from the others. So quite interesting if you are able to produce a decent cost, and you can. This is becoming more and more interesting. Old story, but today more interesting. So the people are just working on this, where you can measure the size of the cavity, and just by making X-rays, and you know exactly what can happen inside here, and the size of the channel in which the things can move. So you can calculate the sizing effect and not the entropic effect. It means which kind of deviation they have to do. Tortuosity, which is a complicated parameters, very difficult to measure really. In this case, it's easy to measure because you can make some geometric analysis, so you know exactly the level of tortuosity which is present, which is one of the factors that we have to introduce in all our equations, and normally we don't know. The tortuosity in the polymeric membrane is something that you learn after. When you don't agree with the prediction, you attribute to the different tortuosity because we cannot measure easily. But that is the problem, and that is not something we can just. Today, people are producing. We have a strong group for the ITM working only on zeolites. And the ladies, they are producing their patent, a new form how to produce homogeneous layer of crystals growing on some support, forming a dense layer. And so you have some new way of doing that. You rotate continuously, for example, your reactors, your tube, such a way that you have an homogeneous distribution during the crystal growth, and that can be done. Or you have what is called a secondary nucleation. You induce some first crystals on the surface, and after you have secondary nucleation, you grow other crystals which are geminated by the first one. So the second layer has some influence and suggestion from the first one already there, and that's make more homogeneous distribution with no defects, because that's the point. You don't want to have one crystal, you want to have a long, homogeneous film, well controlled and dense with no defects in this case, because everything has to go through the windows, has to enter, not between different crystals. We want to avoid this, otherwise gas will move across the different crystals, has to enter in the crystal. So you have such a way that nothing can go. There is no space between two different, not easy to realize, but elimination of small defects that can be achieved by selective cooking or by reaction with silicon alkoxide or other silylation agents. Eventually you can try to block the defects. This is done today, and at the end you can have, this is at the procedures. This is one of the zeolites on the ceramic hollow fiber membrane that we are producing. And you can see here you start from, you buy a ceramic tube, and you clean, you calcinate, you produce certain temperature after you do your mixture, the sodium hydroxide, silicate, sodium aluminate, water, and you just go in autoclave. That's they are prepared by not just as in nature. Zeolites are present, for example, in Naples, where there's volcan. When there are volcans underground, there is a lot of hydrothermal synthesis. That means that these compounds are present underground, high temperature, volcan, and and pressure, and that is hydrothermal synthesis. We reproduce in an autoclave at 90 degrees for 24 hours, and you form the crystal grow, and that is not so easy, but it can be done. And after you dry and go high temperature, and you have this homogeneous distribution. And today, more and more, these are becoming of interest. We mentioned already palladium membranes, remember, and that's quite interesting today, and for the hydrogen problem, so you know already, and there are many other things that we will see in the next occasion, where these hybrid membranes can be optimized for a lot of different kind of separation. There is a big area that is one of the areas in which it makes sense to spend some time to create this mixed matrix system where there's a lot of problems to be solved. The adhesion, the wettability of this inorganic particle or crystal inside the polymeric matrix, and that is one of the problems not easy to just to solve. Carbon nanotubes, that is already another area. The big problem here is how to have this level of orientation. Carbon nanotubes are quite interesting, but for working they are the same as zeolites. You are supposed to enter in the carbon nanotubes. For doing this, they cannot be just mixed. You have to have all the carbon nanotubes ordered in the same way, in this way. Not easy when you have to cast a lot of materials continuously. So you have to find a way of doing this, and that is is part of the work. Okay? We stop here, so otherwise you will make a strike. And we will meet on next Wednesday. And remember, the Wednesday afternoon, there will be also a seminar related to the same topic that we are discussing in class. So if you are interested, also there will be this occasion Wednesday afternoon. We will have a guest, that will be Dr. Tocci. She's the one that will discuss, and she will be here during the week. Some of you already know her. So if there is any other problem or motivation for clarification, discussion, etc., you can, she will be in class, she will give you the seminar, but you can also interact during the days if necessary. Okay? Good? Question, problems? Okay.